You explained the wave function, what a wave function is and what it means, but I'm still having trouble applying it, specifically to find momentum and things like that. I've tried looking it up, but it feels very hand-wavy to me. I think seeing the quiz solutions might clear this up for me. Thank you. Well, thank you. First of all, please understand, again, we're building our understanding of the subject one thread at a time, okay? Wave function describes a particle, and there's a lot of information that we can get from this wave function, a lot of statistical information, averages and so on, including momentum, and if it's in 3D, angular momentum, there are lots of other things. How to extract that information from the wave function, that we haven't learned that yet. What we, the only wave function that we looked at so far, the only concrete example, was a particular solution, one particular solution to the Schrödinger's equation for free particle. Okay, so it was a solution, was a wave function that describes a free particle. Particle doesn't experience any forces. And that wave function was so this is a particular solution to a free particle Schrödinger's equation. Okay, this describes a complex form of a plane wave, meaning the wave fronts are planar. So it has a cosine and it has a real and imaginary part. Let me write it out like that. I think people are still confused about how to separate a complex number or a complex function into a real and imaginary components. But right now is a good time to have that confusion. In any case, these are waves. This is called the wave number. And this is called a angular frequency. Okay. This particular wave function, this particular solution has a pure frequency and a pure wave number. Now, if I have another solution where I combine plane waves with different k, right, and I try to form a wave packet, well, that wave packet now doesn't have a single k because there's lots of k's involved, like you saw in your wave lab. But this one has a single k and a single omega. De Broglie says that, well, P equals h bar k and energy equals h bar omega. So that's the momentum, and this is kinetic energy. Okay. So again, this is a particular solution to a free particle Schrödinger's equation. It's a wave function that happens to have a pure k and a pure omega. Now, in general, wave functions can be quite complicated, and how to calculate momentum and energy from those wave functions we'll learn later. But remember that if a wave function is not made up of a single k, that means that when a measurement is made, you will not always get one and the same k value, one and the same momentum value. And instead, you would get some kind of a probability distribution. Instead, there is a probability distribution to obtain a momentum upon a measurement. Just like there's a probability distribution to obtain a position upon a position measurement. And how to calculate averages, variances, standard deviations, and so on, that we will learn later. Okay? All right. Well, I hope that answers the question. And again, you have to be patient as we are building up understanding, right? So this was a little bit kind of an early example, an example of a wave function that happens to be a plane wave, that happens to have a single k and omega value in it. Okay? Okay, so I hope that helps. And now I want to move on to the main part of the lecture, right? So this is answering. This is this was answering a student's question. Okay, what is it that I want to do today? We are going to switch gears today. Okay, so today we're going to learn how to compute frequencies and properties of standing waves on a string. You might say, well, what's that got to do with quantum mechanics? You have to be patient, and it will become clear that it has everything to do with quantum mechanics. Well, for one thing, quantum mechanics in the form that it's presented here is wave mechanics. So clearly, another example that has to do with waves probably has some utility for our understanding of quantum mechanics. Okay, so here's the question. You have a string. Okay, so okay, so this is a string with some tension T. Let me say maybe T is a bad, let me use a different notation. Force of tension, okay? And a mass density, mass per length. Rho, okay? And the question is, describe the standing wave modes, their frequencies, their shapes, okay? So this is rho. Okay. Question, what are the frequencies and shapes of standing waves on this string? Okay, you know what the standing waves will be, right? So you know this is a possibility. This is review of phys 2. This is a possibility, etc. First of all, how did we conclude that these are the possible standing waves? And if you think about standing waves, you probably remember something that they taught you, that standing wave happens when you have two traveling waves moving in opposite direction. And the only way that this can happen here, it can only happen at specific wavelengths when you can fit in just an integer number of these half wavelengths. Why is that? Because of boundary conditions, because the string has to be attached at the end, right? So this kind of a shape doesn't work because it doesn't obey boundary conditions. So boundary conditions are it's an extremely important thing to keep in mind, okay? So only these forms of standing waves are allowed because of those boundary conditions, okay? Okay, so these are allowed these are called modes of boundary because of fixed boundaries. Okay, Fixed boundaries say that this is allowed, but this is not allowed. Okay, and so then the next thing you say, well, if these are the only possibilities that are allowed, I can tabulate. Okay, so boundary conditions, I'm gonna abbreviate as BC. Boundary conditions dictate allowed wavelengths, right? So if this is of length L, the first wavelength is 2L, the second wavelength is L, the third wavelength is 2/3 L, and this is 2L over 2, and then you can see that nth wavelength equals 2L over n. And what about the frequency? Well, the frequency equals speed divided by the wavelength, so therefore nth wavelength, nth frequency equals v over 2L times n. I have two questions to you. First is, how do you get the string to oscillate in this pattern? Pause the video, think about it. How do you actually get the string to oscillate in this pattern? Because if I pluck the string, it will not oscillate in this pattern. You can pluck the string, you can shoot a video, you will see it will be some complicated mess. Okay? And the answer is, there are two ways to do that. One is if you create an initial distortion of the string that exactly matches the shape of this of one of these modes, and you just let go, and it will stay in that mode, and it will oscillate with this frequency. So if you create an initial condition that looks like this, so this is mode 1, and you just let go, it will oscillate with frequency f1. This is mode 2. And if you create an initial condition of this sinusoidal shape, you let go, it will oscillate with frequency f2. And so you see there's a node here, and there are nodes at the end. And in the first mode, there's one antinode in the center, and in the second mode, there are two antinodes. First of all, this is hard to do, to create such an initial condition. And second, there's usually damping. So even if you do create an initial distortion, it has the shape of, for example, the second mode, you let go, it will very quickly die down because of internal friction, because of friction at the support points. And a more practical way is to apply an external driving force that's a pure periodic driving force, a pure sine wave. And when the frequency of that force, external driving force, comes very close to one of these natural frequencies, the mode will just light up. In other words, it's a resonance phenomenon. Just like if you take a single mass on a spring and you drive it at its favorite frequency, at its natural frequency, it will respond the most at that particular frequency. Same thing here. And if the damping is sufficiently weak, the response will be pretty much extremely strong, exactly at one of these natural frequencies, and it will fall off very rapidly. So if you detune by 1/10 of a hertz, there's hardly going to be any response. At resonance, you're pumping energy into the system in the most efficient way. Away from resonance, your energy input into the string is not efficient, so the string doesn't respond as much. Well, okay, and my question number two is, well, in general, if the string doesn't oscillate in one of these modes, why do I care? This seemed like very special patterns of oscillation. If I just ping, yank the string on a guitar, it doesn't oscillate in one of these modes. What do you think is the answer to that? Why do we care about these things? Yes, in your lab 3 in Phys 2, yes, you did drive a string by periodic force, and yes, it did light up strongly when the driving frequency matched one of these natural frequencies. But why do I care? Why do I care? And this is a very important question. And the answer to that is that it's a very big deal what I'm going to say now. You care because any pattern of oscillation can be expressed as a sum of these very special patterns, the modes, right? So any uh, so first of all, it's a question: how to get a string to vibrate like that? Answer: either prepare it in one of these modes, or drive by an external force at frequency equals f sub n. So question 2 now is, why care? Okay, so in general, if you pluck a string, it will have complicated pattern, right? So, and the answer is that any oscillation of the string can be expressed as a sum of these modes. Okay, this is a big deal. That's why the modes are useful, because they form like bricks, building blocks, bases. So mathematically, any spatiotemporal dynamics of the string, right? So you have this is position x and this is y, right? So the distortion of the string is y at any given x and at any given time. So this is at some moment t1. You can express it as mixing in of these modes. Now these modes are, let me express it like these, like differently. So this is y sub n. Let me do it like this. Okay, so these are modal modes. So this is a mode, and you can express the motion of the string as a sum of each mode, and the coefficients in general depend on time. Okay, if this bothers you, if you don't understand, if you don't feel comfortable with that, that's okay. Okay, just in plain English, this is the same as saying that you can express any distortion of the string, any dynamics of this string as a sum in terms of the sum of those modes. So that's why those modes are useful. And question number 3, these are good questions for you to think about. Why are string modes sinusoidal? It was sort of assumed, it was given to you that they're sinusoidal, right? So this is, if this is x, this is x equals 0, this is x equals L, right? So y sub n, y sub 1 of x was given by it was given to you by what, sine 2 pi x over lambda 1, right? So that's this. Y sub 2 of x equals sine of 2 pi So the second mode is 2 pi times x over lambda 2, and so on. But why sine? You probably have not thought of this question. Not all things are sine waves. You know what? I will tell you something. If you go to Home Depot and you buy one of those thick, long wires, I'm not sure what the technical name for the gauge of that thing is, right? So if you take a rod, right? If you take a rod, right, and you clamp the rod, so this is a cylindrical rod, and you clamp that cylindrical rod at both ends, it also has modes, right? But those modes are not sinusoidal. Those are non-sinusoidal modes. This also has modes, but they are not sinusoidal. And the reason they're not sinusoidal is because the mechanism of restoring the mechanism of the restoring force is different. In the string, it's the tension. Okay, the tension is trying to restore the string back to equilibrium, but because the string has inertia, it always overshoots the equilibrium. That's how you get oscillations. In the case of a rod, the restoring force is not the tension, but the fact that when you bend the rod, one part of the rod is compressed and the other is stretched. So the stretched part wants to compress and the compressed part wants to stretch. Okay, so it's a bending, it's a bending of the material itself is what causes the rod to try to restore back to equilibrium. But again, it has inertia and it overshoots. So these are different mechanisms of restoration. So it's different physics involved. And they're described by different equations of motion. So in general, modes are not sinusoidal. And by the way, I keep talking about modes, like what are modes? What defines a mode? By the way, what is a mode anyway? And the answer, it's a solution in which every point on the object, string, rod, drum membrane oscillates in phase and with the same frequency. That's just my own definition. It's a pattern of vibration, sorry, it's a pattern of vibration. You might say, well, if a string is in this second mode, isn't this point and this point out of phase? Well, you could say that they have negative amplitudes, right? So, I mean, you can get technical. You could say that they're either in phase or pi out of phase, but that's a technicality. We can just say that this has a negative. When this has a positive displacement, this has a negative displacement. So this is a pattern of oscillation where every point is in sync with every other point. Okay, and in general, if you pluck a string or if you bang on this rod, it will oscillate in some complicated pattern that's not a modal pattern. What I want to do today is I want to discuss how to compute modes on a string properly. That will answer the question of why the modes are sinusoidal. And that will give you another perspective of how to get the frequency, and will also give you a deeper understanding of what a mode really is And if we have time, we will also see how you can superpose modes to get a general solution. So I'm going to stop this video, and in the second part, we will start that discussion, okay? All right, in the meantime, it's not a bad idea for you to review standing waves on strings from Phys 2, all right? Okay.